Hello there, I'm Mohammed Haziq, and me and my team are going to present our integrated design project of a plant for producing methanol. So from group 3A, so I'm going to give Harshini to to introduce the principle of chemical engineering.
My name is Harshini, and this is the Introduction to Principles of Chemical Engineering. So, methanol is a simple alcohol with a boiling point of 64.7 degrees Celsius, widely used as a solvent, antifreeze, and chemical intermediate, and is gaining importance as a clean burning fuel and hydrogen carrier. Two main production routes are considered, which are the conventional method using steam methane reforming to produce syngas, and the greener alternative of hydrogenating captured CO2 with green hydrogen from renewable powered electrolysis. CO2 hydrogenation is an exothermic process operated at high pressures and moderate temperatures, which are facilitated as Cu-based catalysts that promote the conversion of CO2 through a formate pathway. Catalyst performance can be enhanced with promoters like zinc oxide that support such as MOFs or spinels, and ongoing research in exploring energy efficient techniques like chemical looping and membrane separations. Designing a methanol plant involves applying core chemical engineering principles such as material and energy balances, thermodynamics, transport phenomena, reaction engineering, process control, and economics to ensure efficiency, safety, and sustainability. While the green pathway faces thermodynamic limitations, it offers significant environmental benefits. Process design focuses on integrating reactors, heat exchangers, and separation units while balancing costs, catalyst longevity, and environmental policies such as carbon pricing. Ultimately, the goal is to produce methanol efficiently and sustainably, which supports the global shift toward a low carbon and circular economy.
Hello there. So I'm going to explain about the process flow diagram of a plant for producing methanol. So at first, comes from the feed one and feed two, which is the feed one is the carbon dioxide, and the feed two is hydrogen. We'll go into the mixer, and we'll go to the compressor, and we'll go to the heat, and then go to the Gibbs reactor, and go to the cooler, and we'll go to the separator, and we'll be separating the gases and the liquid. The gases will go to tank one, and the liquid will go to the distillation column for distillation, of course, and we'll get stream 8 to tank 2, which is the methanol, and the remaining substances that we use that we need to recycle, which is the recycle stream, which will be going to the mixer. So now I'm going to explain the function of each unit operation. Let's go. Alright then, so we'll start with the feed 1 and feed 2, which is the carbon dioxide and the hydrogen. They will, of course, they supply the reactants streams for methanol production. And the second unit operation is the mixer. So the mixer combines the feed one and feed two into a single well mixed stream to ensure consistent input to composition before compression. So from the mixer we go to the compressor for compression. Alright, so the compressor, the third one. The function is to increase the pressure of the feed stream to meet the operating pressure required for efficient methanol synthesis. Why is this? Because methanol synthesis occurs more favorably at higher pressure. So we need high pressure, which is we need the compressor to make the pressure high of the stream. Okay, so the fourth is the heater, which is the function is to raise the temperature of the compressed gas to the desired reaction temperature. Why is this? Because the methanol forming reaction is endothermic, and it requires elevated temperatures. So that's why we need heater. Okay, and then we got uh, Gibbs reactor. So Gibbs reactor is to stimulate the methanol synthesis reaction. So the chemical equation that we get is there's carbon dioxide plus hydrogen. We will get methanol and water. So this Gibbs reactor is and equilibrium based. So it finds the composition that minimizes Gibbs free energy. So uh, the cooler, the sixth one is the cooler. So the cooler is to reduce the temperature of the reactor output. This is to condense the methanol and water. Why is this? Because condensation allows phase separation in the next step. Because we'll go to the separator after the cooler. Alright then, so for the separator, the function is to physically separate the gas and liquid phases of the cooled reactor effluent. So we'll get stream 6 and stream 7, which is stream 6 is the gas that consists of unreacted gases like hydrogen and carbon oxygen, and the stream 7, which contains condensed methanol and water. Right, so then from this stream 7, we'll go to the distillation one, which is the unit operation, the eighth unit operation. The function is to separate the methanol from water and others. So we got the stream 8. So from that, we will get the cycle stream also, which is the unconverted materials that can be directed back to the mixer for reuse. So and the ninth is the tank one. So it collects the unreacted gases, mostly hydrogen and carbon dioxide, which can be vented, used, or sent for treatment from the separator, right? And the tenth one is the tank two for the stream eight, which stores liquid methanol product. So we need methanol, right? So we store it there in the tank two. All right then. So I'll give to Harshini.
For the compressor, the assumption in the S1 stream is that mole flow for hydrogen is 300 kmol per hour and mole flow for carbon dioxide is 100 kmol per hour. The molecular weight for hydrogen is 2.02 gram per mole and the molecular weight for carbon dioxide is 44.01 gram per mole. The mass flow rate for hydrogen is 606 kilogram per hour and the mass flow rate for carbon dioxide is 4,401 kilogram per hour, whereas the mass fraction for hydrogen is 0.12103 and the mass fraction for carbon dioxide is 0.87897. The mole flow, mass flow, and mass fraction for hydrogen and carbon dioxide remains the same after exiting the compressor. For the heater, the total mass in is the same as total mass out. The mole flow in is equals to mole flow out, mass flow in equals to mass flow out, and the mole fraction in is equals to mole fraction out. This applies for each of the components.
This slide presents a non-reactive mass balance typically used in chemical engineering to ensure masses conserved in systems where no chemical reaction occurs. For example, like in the distillation columns or mixing processes. So as you can see, for the mixer, I calculated the total inlet flow, which was 400 kilomole per hour, and then I calculated the component molar flows, molecular weight, total mass flow rates, and then I got the total as 5,000 kilogram per hour. And I also calculated the mass fraction for CO2 and H2. I got for CO2 0.88 and for H2 0.12. And then the distillation column table, I have 4 components. I calculated the mole fraction, the molar flow, the mass fraction, and also the mass flow. And then the last one, which is the distillation column for the non-reactive mass balance, it was already solved in the slide, but I just did the balance check for H2, CO2, methanol, and water. So all of them were balanced, as you can see. So all in all, the components are mass balanced, meaning that the total N is equal to the total out, as expected for a non-reactive mass balance.
The calculations for the reactive system involves the Gibbs reactor, and based on the calculations shown here, it is proven that the hydrogen, carbon, and oxygen balance is the same when entering and exiting the reactor.
Distillation column, molar flow rate for inlet is hydrogen is 8.95 times 10 to the power of negative 3 mole per second. Carbon dioxide is 0.0154 mole per second. Ethanol is 0.7202 mole per second, and water is 2.3549 mole per second. For the enthalpy inlet for hydrogen, carbon dioxide, methanol, and water are 0 kJ per mole. The molar flow rate outlet of the top for hydrogen is 7.12 times 10 to the power of negative 3 mole per second. Carbon dioxide is 0.0122 mole per second, and water is 1.8652 mole per second. For the molar flow rate for outlet bottom of methanol is 1.0200 mole per second. The enthalpy for outlet of top for hydrogen is 53.37 kJ per mole. Carbon dioxide is 52.79 kJ per mole, and water is 0.04 kJ per mole. The enthalpy for outlet of bottom methanol is 0.09 kJ per mole, and the heat transfer is 1.1897 kJ per mole. For mixer, the molar flow rate for inlet of the top of hydrogen is 83.3278 mole per second. The molar flow rate for inlet bottom of carbon dioxide is 27.7775 mole per second. The enthalpy of inlet for top and bottom of hydrogen and carbon dioxide are both 0 kJ per mole. The molar flow rate outlet for hydrogen is 517.2898 mole per second, and carbon dioxide is 7.8986 mole per second. The enthalpy outlet is for hydrogen is negative 2.88 times 10 to the power of negative 4 kJ per mole, and carbon dioxide is negative 3.72 times 10 to the power of negative 4. Heat transfer is negative 0.1519 kJ per mole. For compressor, the molar flow rate for inlet of hydrogen is 82.7664 mole per second. Carbon dioxide is 27.8032 mole per second. The enthalpy for inlet for both hydrogen and carbon dioxide are 0 kJ per mole. The mass flow rate for outlet of hydrogen is 82.7664 mole per second, and carbon dioxide is 27.8032 mole per second. The enthalpy for outlet of hydrogen is negative 41.16 kJ per mole, and carbon dioxide is negative 32.42 kJ per mole. The heat transfer is negative 4308.04 kJ per mole. For heater, the molar flow rate for inlet of hydrogen is 517.2898 mole per second, and carbon dioxide is 7.8986 mole per second. The enthalpy for inlet for both hydrogen and carbon dioxide are 0 kJ per mole. The molar flow rate for outlet of hydrogen is 512.2898 mole per second, and carbon dioxide is 7.8986 mole per second. The enthalpy for outlet of hydrogen is negative 8.32 kJ per mole, and carbon dioxide is negative 13.78 kJ per mole. The heat transfer is negative 4412.69 kJ per mole. For cooler, the molar flow rate for inlet of hydrogen gas is 496.5982 mole per second. Carbon dioxide is 7.5827 mole per second. Methanol is 0.8680 mole per second, and water is 1.5436 mole per second. The enthalpy inlet for hydrogen, carbon dioxide, methanol, and water are 0 kJ per mole. The molar flow rate for outlet of hydrogen is 496.8982 mole per second. Carbon dioxide is 7.5827 mole per second. Methanol is 0.8680 mole per second, and water is 1.5436 mole per second. The enthalpy for outlet of hydrogen is negative 6.66 kJ per mole. Carbon dioxide is negative 9.85 kJ per mole. Methanol is negative 24.81 kJ per mole, and water is negative 8.29 kJ per mole. The heat transfer is negative 3416.33 kJ per mole. For separator, the molar flow rate for inlet of hydrogen is 496.5982 mole per second. Carbon dioxide is 7.5827 mole per second. Methanol is 0.8680 mole per second, and water is 1.5436 mole per second. The enthalpy for inlet of hydrogen, carbon dioxide, methanol, and water are 0 kJ per mole. The molar flow rate for outlet top of hydrogen is 485.8595 mole per second. Carbon dioxide is 7.5190 mole per second. Methanol is 0.4131 mole per second. The molar flow rate for outlet bottom of carbon dioxide is 0.0152 mole per second. Methanol is 0.7301 mole per second. Water is 2.3373 mole per second. The enthalpy for outlet top of hydrogen, carbon dioxide, and methanol are 0 kJ per mole. The enthalpy for outlet bottom of carbon dioxide, methanol, and water are 0 kJ per mole. The heat transfer is 0 kJ per mole.
Alright, now, so here is I'm going to talk about the energy balance for reactive systems. So we have one reactor system, that is the Gibbs reactor. So first we need to do the PFD of itself, the Gibbs reactor, and then we need to do to label all the components in the input and the output of the reactor. And then we need to do the chemical equation, and it must be balanced, and the coefficient of the chemical equation for each substances. And after that we need to get our extent of reaction. This is because we need to do the heat of reaction, and we need to use it to find the heat energy. Okay, so we need to find the heat of reaction using the formula, and then once we got it, we need to do a specific enthalpy table. So the specific enthalpy table uh, is to categorize. It makes us know which objectives are we going to do first to last. If you can see from H1 until H10. Right. So let's go to the next one. Alright. So to do the energy balance for this one, we need to have reference points. Why I said reference points? Because each species we need one reference point. So we have four species, which is hydrogen, carbon dioxide, methanol, and water. So we need to have four reference points. So for hydrogen and carbon dioxide, we have vapor 35 degrees Celsius and 1 atm, and for methanol and water, we have liquid 25 degrees Celsius and 1 atm. This because all the 25 degrees Celsius is because we are using standard temperature. And then we will do from delta H1 until H10 to find the uh, specific enthalpy. Alright then, so once we got all the specific enthalpies, we need to do the energy balance equation. So energy balance equation is delta H plus the delta kinetic energy plus the delta potential energy equals to heat energy, or the energy plus the work. So we need to cancel out the kinetic energy, potential energy, and the work because it is stationary. It is not moving. Alright, so we will have then delta H equals to Q. So specific enthalpy equals to heat energy. So to find the heat energy, this is the formula, and just put all the information that we got, and then we will get heat energy that is plus 91,612.3433 kilojoule per second. So it is an endothermic reaction, like I've said before. It is an endothermic reaction because we're producing methanol. Okay, so this is the specific enthalpy table that once before is not complete. Now we have completed it. So yeah, I'm going to give to Harshini for the conclusion.
In conclusion, the design of a methanol production plant showcases how fundamental chemical engineering principles, like material and energy balances, thermodynamics, transport phenomena, reaction engineering, and economic analysis, come together to ensure safe, efficient, and sustainable operations. Methanol itself is a highly valuable industrial chemical, and it's also gaining attention as a clean energy carrier and alternative fuel. In this design, we compared the traditional syngas-based synthesis route with a more sustainable CO2 hydrogenation pathway. While the green route poses thermodynamic challenges, it offers clear environmental advantages by utilizing captured CO2 and green hydrogen. Through both reactive and non-reactive system modeling, we conducted accurate mass and energy balance calculations to guide optimization. Catalyst performance was a key focus, especially the use of Cu-based systems that are promoted by zinc oxide or supported on advanced materials, all integrated with thoughtful reactor, heat exchanger, and separation unit design. The broader goal remains sustainably enhancing CO2 utilization, improving energy efficiency, and minimizing emissions, which ultimately reinforces the critical role that chemical engineers play in driving innovation toward a low carbon and circular economy.